You're probably familiar with several technologies which use radio frequencies. These technologies include many common things such as AM radio, FM radio, Wi-Fi, radar, and even light bulbs. The complete range of all electromagnetic radiation is called the electromagnetic spectrum, and Wi-Fi is often simply called spectrum without the reference to electromagnetics. A sine wave is a curve that describes a smooth, periodic oscillation which represents energy entirely concentrated at a single frequency, such as with wireless signals. As shown here, sine waves have some basic properties. The first two we will discuss are amplitude and wavelength. Amplitude is the distance from zero to the maximum positive and negative alternation, which are the same distance. The period of the wave is measured by how long it takes to complete one entire cycle. Wavelength is the distance traveled by the sine wave during the period and is indicated by the Greek lambda symbol. It is the distance between one value to the same value on the next cycle. Amplitude. Amplitude means power in RF discussions. Amplitude is the height, strength, or power of a wave. The higher the output power, the higher the amplitude of the wave. Amplitude can be controlled by turning the signal on and off, or by varying the signal strength of a wave. Some common units of measure for amplitude, or RF signal power, are watts, milliwatts, and decibels measured. When you see dBm, it means decibels measured, and can be used as a power level. Decibels are a measure of change. In Wi-Fi, we reference 0 decibels measured to 1 milliwatt as our starting point. Amplitude is the amount of signal energy. It is the strength or power of the signal. Wavelength is the distance traversed during one oscillation or cycle. This can be measured at any point in the waveform, so long as it is measured at the same point on each oscillation. The lambda symbol is used to represent wavelength. Wavelengths of RF signals used in wireless networks can be physically measured in centimeters. 2.4 gigahertz waves are longer, allowing them to travel and be usable at longer distances than 5 gigahertz waves when using the same transmit power. Frequency is the number of times that a wave oscillates within a period of time. For wireless communications, frequency is measured in 1-second intervals. One oscillation in a second is known as a hertz. 2.4 gigahertz signals oscillate around 2.4 to 2.5 billion times per second, and 5 gigahertz signals oscillate around 5 to 6 billion times per second. Understanding wavelengths and waveforms will give you a better understanding of Wi-Fi propagation. Lower frequencies have longer wavelengths. Higher frequencies have shorter wavelengths. When you know the wavelength of an RF wave within a given frequency range, you can optimally design and select antennas for that range. Lower frequency signals are able to penetrate some materials better than higher frequency signals using the same power, in addition to be able to go farther given the same conditions. This is why 2.4 gigahertz transmissions can be used in areas where 5 gigahertz signals may fail. In the wavelength and frequency calculations, the constant c is the speed of light, roughly 300,000 kilometers per second. When the frequency changes, the wavelength changes. When the wavelength changes, the frequency changes. This is because the wave is moving or traveling at the speed of light. Wavelength and frequency are inversely related. Lower frequencies have longer wavelengths. Higher frequencies have shorter wavelengths. If the wave cycles more times per second, it is because it is a shorter wavelength that must travel the same distance in the same amount of time as a longer wavelength. If the wave cycles fewer times per second, it's because it is a longer wavelength that must travel the same distance in the same amount of time as a shorter wavelength.